the 3-7 notes for Calculus 1. This section really starts to push towards the more involved derivatives. We learn a rule called the chain rule, which allows us to basically enhance the type of derivative that we can find. Before this, we could only really tackle the derivatives for a handful of functions. Most of them pretty simple, even though I know some of you will probably look at me sideways because of some of the product and quotient rule problems that we did. But this section pushes it a lot farther, and by the end of it, we'll pretty much be able to tackle most functions and their derivatives. Before we get into the actual chain rule itself, let's talk about something from algebra, a little bit of a review, called the concept of composite functions. So composite functions are famously known for basically being able to take one function and put it inside the other one. So for what you would have seen in the past, you would have seen something like this. F of g of x. So basically I have a function f, and then I want to take the function g of x and put it in for wherever I see x. So g of x for wherever I see x. So just as I want to do a little bit of an algebra example here, just to make sure everybody remembers this and all is good, you should have done this when you did inverses in pre-calculus. You should have reviewed this, but it just depends on whatever course you took and where you took it. So just look at an example here. It says, let's say f of x is root x, and g of x is x squared plus 1. Then let's say we want to find f of g of x. So we normally have f of x, but now it's saying take g of x and put it in for wherever we see x in f of x. So our f of x is root x. We now need to take our g of x and put it in where you see x. So if we do that, we would get the square root of x squared plus 1. So this is, it's a little bizarre, right? But it is basically just called composition. That is the formal name for what you're supposed to do. But that is an extremely important part of the chain rule, because a lot of functions that we know of are composed. They are already part of a composition. Believe it or not, you have not done any problems other than a few that could be shortcutted a little bit that have dealt with functions within other functions. It was something like e of x cosine of x. So note, all it is an x here. There's nothing like e to the 2x plus 1 cosine of x squared minus 2. There's no functions within other functions. So now we are able to actually expand that and use a new rule called the chain rule in order to do so when finding derivatives. Okay, so the chain rule is defined by the following formula. We're going to use this explicitly for a while, but generally you're not going to even have this you're not going to need for this to be memorized. It's just going to be second nature to you to just do it, and even though you might not understand that now, you will soon. Basically what it says is if you take the derivative of a function that is composed, or in other words, a composite function, one inside another, I call this the outer function, and I call this the inner function. Then according to this, the true derivative of this by the chain rule is taking the derivative of the outer function with the inner function still composed inside of it, times the derivative of the inner function. That is the process. Now, that's why I call this the outside-inside method of finding derivatives. It's a very good sort of summary or description of what you would actually do. Okay, so I start with doing just basic examples here, And when I get to normal examples later on, like when we're doing 1, 2, the whole 1, 2, 3 thing down here, it'll be more of a shortcut process. But for now, we're going to learn this pretty slowly to make sure all is good. This is one of the most important sections in the entire textbook because most derivatives use the chain rule. And most of that you're going to use from now on will use the chain rule, so it's really hard to move on unless you know this. So let's talk about how we break this down. So look at the function. We have cosine x squared plus x. Okay, note if you were just given cosine x, you would easily be able to find the derivative without the chain rule, negative sine x. There's not really any function embedded in the function, it's just a generic function. So now we have another function, x squared plus x, that is now embedded in the cosine function. So let's identify the outer and inner functions. First, I usually do the inner function first. If you look at the graph, what function is embedded in the other one? Well, clearly that's x squared plus x. In terms of the definition up here, we represent the inner function as g of x. So I'm just going to write that there. Well, what's the outer function? Well, the outer function is the one that basically encloses the other function. So that's going to be cosine x. So that is going to be our f of x for the purposes of our problem. So what do we need in order to find all the pieces that are up here, right? What do we need? We need the following. Next, determine the derivative of the outer function. All right, so we got our outer functions right here. What's the derivative? So you have learned that the derivative of cosine x is negative sine x. But once we know that that's our derivative, we now need to find that derivative, but with g inside of it, the composite function. So if we took this function right here and we composed it with x squared plus x, what would that look like? I would take negative sine and then I would put x squared plus x wherever I see x, and I would get that. So that is f prime of g of x. Next, find the derivative of the inner function. Okay, so the inner function is over here. So the inner function's derivative, it looks like it's going to be 2x plus 1. So if you look really carefully here, what have we found? Well, look at this and look at this. Well, our formula states that the derivative of f of g of x is the product of the two values that you see above us, above this. So what does that mean? That means that we officially can just simply do this. The derivative of our composite function is going to be negative sine x squared plus x times 2x plus 1. So this literally is the answer to our problem. That is the derivative of our function cosine x squared plus x. Now note, this is a little misleading, only because, not misleading, but students often struggle a little bit with this because what they'll see is, they'll see this next to each other. So what do you think their instinct is to do here? It's to FOIL, and that's absolutely something you cannot do. You cannot FOIL because this x squared plus x is basically inside the sine function and cannot be multiplied by anything else. So this is often written a different way to avoid confusion. Instead, the negative, this 2x plus 1, is often thrown to the front. And we get something that looks like this instead. I am fine with you providing either answer, but I just wanted to point out that the second one is more similar to see in an answer key, let's say in the textbook or in the back of the book when the answers to the odd problems. So just worth noting when it comes to that, but this is an example of using the chain rule in order to find derivatives. Essentially, find the derivative of the outer function, leave the inner function, then multiply that by the derivative of the inner function. Okay, more examples. I want to do my best to make sure all of this is good. It says differentiate e to the 8x minus 3. Okay, so you have learned the derivative of e to the x. You've learned the derivative, the shortcut formula for the derivative of e to the 8x. but you do not know what to do when there's a binomial in the exponent place. So we now need to use a new method basically called the chain rule. Now note, you can also use the chain rule for this, but you hadn't learned it yet back then, and the author wanted you to use e to this kx early. Worth noting, that's not too important, but what do we need to do? We have to identify the outer and inner function. So again, when I say e to the 8x minus 3, which one of these function is the inner function, the one that's inside the other one? Sometimes this is tricky for students, but it should be pretty clear that 8x minus 3 is the function that's inside the exponential. It's in the exponent of the exponential, which means the outer function is just e to the x. So one of the things as a shortcut we can use to identify inner functions is they often are either in parentheses inside a function, or they're in exponents inside a function. So this is not always the case, but this is an excellent shortcut for identifying them. Okay, so what do we have to do again? We have to find the derivative of the outer function. The derivative of the outer function e to the x is just itself e to the x. What is the derivative of e to the x, that function, but with g of x inside of it? Well, we need to take this guy and put him in there. So e to the 8x minus 3. Next, what is the derivative of our inner function, 8x minus 3? It's just 8 minus 0, which is 8. So therefore, again, if we want to find the derivative of this composition, we have to take this and multiply them out. So what does that look like? E to the 8x minus 3 times 8. Well, this one is not an or. This one you really need to change. You wouldn't write this way. You would take the 8 and put it in front. So the derivative is 8e to the 8x minus 3 for our chain rule. One small thing though, what I often get from students after this is they try to make a shortcut. So they go, well, if the derivative of e to the 8x is 8e to the 8x, and the derivative of e to the 8x minus 3 is again 8e to the 8x minus 3, then they'll often do something like this. Let's say 2x squared minus 1. They'll be like, well, isn't this going to be 2e to the 2x squared minus 1? Well, believe it or not, it is not going to be that. So be careful with shortcuts with doing these problems. Literally just follow the chain rule and you will always get what you need to get out of the problems. Okay, so we're going to pick up the skill level a little bit. Some of these problems are going to get a little tricky for understanding, but again, these are very straightforward examples of what you're going to be doing very commonly throughout the rest of the course. How about we find the derivative of 3x squared minus 4 to the 5th power? Okay, so you know how to find just x to the 5th power, but what if I plug in 3x squared minus 4 in for our x and get this composed function? Well, it's going to be a little bit tricky to understand this one, but let's give it a try. So first of all, what's the inner function? What's the one inside the other one? Well, again, I gave you a shortcut before. It's usually what's inside the parentheses, which is 3x squared minus 4. It makes sense because we're doing something to this quantity. Now, the outer function. Okay, I usually ask this in class, and this is the first stumper I get with students, where students are like, well, what are we actually doing in the function itself to the inner function? We're taking it to the 5th power, which means if we replace this with a generic x, that would be the outer function, x to the 5th. Similar to what I wrote over here a second ago, x to the 5th. So we have an outer function, which is something to the 5th power, and we have an inner function, 3x squared minus 4. So let's go ahead and do the process. So what's the derivative of the outer function? It is 5x to the 4th. What's the derivative of that same function, but with g inside of it? 3x squared minus 4 to to the fourth. So all I did was take this and put it in right there. What about the derivative of our inner function? That looks like it's going to be just 6x, which means if I want to find the derivative of the composition, I'm going to take the first one and multiply this guy and multiply by this guy. Again, you wouldn't leave it that way. You would move the 6x to the front and get 30x times 3x squared minus 4 to the fourth. Okay, and that is our derivative. Now, note also, I gave you some shortcuts with the quotient rule for leaving things the way they are. Don't do that with the chain rule. There are problems where you will have to take the chain rule again. So you're not going to be, I know, yes, some of you are like, what? Yes, you're going to have double embedded chain rules eventually, maybe even in the section. I'm going to show that to you. So you need to simplify them. That does not mean multiplying out the fourth. That's insanity. You don't have to do that by taking that to the fourth power, but simplify easy things, right, in order to make sure that you get a very clean looking equation. Okay, so last example before we jump into just a billion problems, all types, shapes, and sizes. Okay, so we have a radical problem, the square root of x squared plus 1. Okay, so if you remember, that was the first composition that I showed you all the way in the beginning right here. So we said, well, what if we took root x and x squared plus 1 and composed them? We would get the square root of x squared plus 1. So what if we wanted to find the derivative of that? So let's take a peek. So a radical is like a parenthesis. So the inner function is clearly going to be x squared plus 1. Which means the outer function is if you replaced x squared plus 1 with x, what would you get? You would get root x. Okay, so what is the derivative of the outer function? So this is more in depth than just easier size. So I told you that you should memorize the derivative of root x. And why? Because of the chain rule. And I'll explain that a little later. But the derivative of root x is 1 over 2 root x. Note, you cannot memorize, there is no fancy memory. I mean, technically you can memorize cube x and fourth x. But you don't use them enough to have to memorize that. But you get 1 over 2 root x. Now, some of you who are maybe not as great with this math stuff might be like, where did that come from? So just to be clear, remember root x is x to the 1/2. So if I find the derivative of that, here was the process. 1/2 comes to the front, x, subtract 1 from the 1/2 and get negative 1/2. Therefore, 1 over 2x to the positive 1/2, which is 1 over 2 root x. We've already done this in a previous section, but I said, you know what, you should really memorize the derivative of root x because that will help, and it will help a lot when it comes to the chain rule sections. All right, so what do we need to do? We need to take this same derivative, but plug in g of x for x. So 1 over 2 root x squared plus 1. What about g prime of x? Well, that looks like that's 2x. So if I'm finding the derivative of the composition, I'm doing 1 over 2 root x squared plus 1 times 2x. So that means the 2's are going to cancel out, and I'm going to get x over the square root of x squared plus 1 as my derivative. All right, so we went through a lot of these problems using this very long drawn-out method, but the reality is you cannot keep up with that. We need to be able to talk this out in a quicker way. So this is the best way in the beginning to really, for me, to learn what you need to do. But as we go through the rest of these problems, I am going to quicken the process significantly. So some of you it will be a little tough, but the goal is to get used to it as soon as possible. The good news is that I do a ton of problems. So we're going to do 10 problems over the next 2 pages in order to make this go as easy as possible in terms of finding derivatives. Okay, part of the problem, so if we look at number 1, actually if you look through 1 through 4 as a whole, you'll see sine 3x, sine x cubed, sine cubed x, sine cubed 3x. So what am I doing? I'm being very anal about showing you the most important concepts involved with the chain rule and how all of these functions that look similar to one another have vastly different derivatives based on how we cover how we use the chain rule for each one and how the functions are actually composed, because they actually do have a different setup for each of them. But the chain rule doesn't change. That's the key in terms of this. So look at number 1. So if we want to find the derivative dy dx, then we have to find the derivative of sine 3x, right? So we'll probably skip this in the next couple problems, but let's be very clear in the beginning. So how do we do the chain rule in a very quick and easy way? Well, the first thing you want to do is you want to identify the outer and inner function mentally. So the outer function is here, obviously, sine, and the inner function is going to be 3x. So what do? How do we find the derivative of this using the chain rule? So this is the best way for you to verbally go through it. First, find the derivative of the outer function with the inner function inside. What is the outer function? It is sine, so therefore the derivative of the outer function is cosine, but we must keep the inner function in place. In other words, it's basically going along for the ride. That is our first step. That is our, by the way, our f prime g of x step. Then we always multiply by the derivative of the inner function. So remember when I told you in product and quotient rules that even though you're not going to wanna, you better write this out? It even gets worse now. Don't skip writing this step out. Make sure you write ddx of the inner function when you go about doing this. So this is g prime of x. And I am fine if you're writing this out, doing the shortcut, and just writing 3 as the derivative. So if we were to combine this, the 3 would go to the front, and this would be 3 cosine 3x as the derivative of this function. So again, what do we always do? We do the derivative of the outer function with the inner function coming along for the ride times the derivative of the inner function. That is the process that you must follow in every chain rule step. Okay, so number 2. I'm going to do 2 and 3 not at the same time, but we need to discuss them at the same time. Why? Because 2 and 3 are completely different concepts. So this problem right here, y equals sine cubed x, it's very important. Let me do it in a different color so I separate this. It's very important that you understand that this is the same as sine x cubed. Okay, whereas this up here in number 2 is essentially the same as sine x cubed. Okay, students struggle with this because they appear the same, and it will confuse the hell out of students. So students will look, for example, they'll look at this here and this, and they'll be like, well, aren't these the same? They're not. So it's important in the beginning here that you completely understand how to write these, because if you look at these two functions now, hopefully they're just leaping out the page at you that it's a completely different composition. That is the key. So look at number 2. So again, we need to find the derivative, right? So let's skip this step here. Don't worry about this. Let's go right to it. So we need to find the derivative of the outer function. Well, the outer function is clearly sine in this problem, and this is the inner. So the sine derivative is again going to be cosine, but what do? We bring along the inner function along for the ride. Then we multiply by ddx of the inner function. So a little bit of shortcut work. So instead of writing this out, we can just do quickly, the derivative of x cubed is 3x squared. Now, we bring it all together by putting that in the front, 3x squared cosine of x cubed. this is the derivative of our function. Okay, so number 1 and 2 are similar because sine is the outer function and the inner function is 3x x cubed, each one, so they are similar in nature, but they create a different problem. But when we move to 3, that all changes. So if you look at 3, when we need to identify outer and inner function, life is changed. Sine is now the inner function, and the exponent, or the power, is now the outer function. So what does that mean? So this is where things get a little crazy. So the outer function is essentially generically x cubed. So if we need to find the derivative of that, this is what we're going to do, but we're going to do it with sine x inside of the function. So where's the 3 go? It goes to the front, and then what do we do to the exponent? We subtract 1 from it. So we get 3 sine x squared. Well, how do we know to do that? Well, if it was x cubed, 3 would go to the front, and we would get 3x squared as our derivative. But what are we doing? We're taking sine x and we're putting it inside. So instead of doing all of that, we're shortcutting the process. We're saying, all right, let's take the derivative while sine is just coming along for the ride. 3 to the front, subtract 1 from the exponent. Multiplied by the derivative of our inner function sine. So what do? We take the derivative, which is cosine. A little bit of a shortcut action there. So what would be ideal? So we're going to get 3. We're going to change this back to where the exponent's supposed to go. Sine squared x, and we can leave cosine where it is in the problem. So look at this. The derivative of sine cubed x is 3 sine squared cosine. Very complex, but that is the derivative using the chain rule. Okay, folks, so hopefully, I'm crossing fingers here, by this point you're getting the hang of this, because we're about to go to a problem that is a whole different can of worms, so to speak. So, this is going to be much different. So, dy dx. We need to find the derivative of sine cubed 3x. So basically, it's kind of a combo platter of 1 and 3. So the key is anytime you ever see an exponent on a trig function itself, you always want to rewrite it like we did over here. So what is this the same as? It's the same as sine 3x quantity cubed. Please do this. If you don't do this, you'll probably be confused. Some students are good at this and they won't be, but most students are very confused until they rewrite it. Because once you rewrite it, it should scream at you that sine 3x is the inner function and the exponent power function is going to be the outer function. So if that's the case, we can go right to getting work done. So what do? We take the derivative of the outer function, which involves 3 going to the front, subtracting 1 from the exponent, 3 sine cubed x squared, leaving the inner function along for the ride, multiplied by the derivative of sine 3x. Okay, so note that, again, we're writing this out for a reason, and I'll show you why right now. So what'll happen is you'll start going, okay, I'm going to do my little shortcut thing here, and then students will be like, oh, this is cosine 3x, I'm done. Okay, wrong. Very, very wrong. Because look at what the first problem was. Our first problem was the derivative of sine 3x. And what did we need in order to do that? We needed, the chain rule. Which means this is a double embedded chain rule. We need to do the chain rule again. So if we're doing it again, what does that look like? So this is where students start going, oh boy. Well, if we look at sine 3x, the sine is now the outer function, and 3x is the inner function. So all we're doing is this over again over here, but I'm going to write it out anyway. So what's the derivative? So this, by the way, what's going on over here just stays put. It's a part of our derivative, but it's done. There is no ddx on it. There's nothing to do there. Here, we have to use the chain rule again. So what's the derivative of sine? It's cosine. We bring along the inner function for the ride, and we multiply by the derivative of the inner function 3x. Well, we know that that is 3, which means now we have this, and this as a part of our derivative. What does that look like? Well, the 3 goes to the front and multiplies by the 3 and gets 9. We have sine squared 3x, and we have cosine 3x, which means, yes, this derivative is this crazy 9 sine squared 3x cosine 3x. So that was by taking all of our found derivatives and putting them together all by multiplication, right? And finding the result. So this one is a doozy, but you have to be able to do all of this without worries. So I would say that for a lot of you, there's going to be a lot of practice that's going to go into this section because you have to be able to do all of these. So let's talk about more other examples that are just randomly given to you. Okay, so number 5. It says y is equal to 5x to the 4th plus 2x cubed minus 8x to the 10th. Part of the chain rule is being able to identify a composition. So if this was just x to the 10th, it's not a composition, it's just a simple function, but we clearly have a function within a function right here. So what are we going to do? We have to find the derivative, and so let's speed up the process here. So what is the outer function? It is the power to 10. So what do we do to find that derivative? We take the 10 to the front, we bring along the inner function along for the ride, we subtract 1 from the exponent, and then we multiply it by the derivative of the inner function. Okay, we can do a little bit of a shortcut here. So this is going to be 20x cubed plus 6x squared minus 8. So therefore, in multiplying and figuring out the rest, we don't really have to move anything. We can just write 5x to the 4th plus 2x cubed minus 8x to the 9th times 20x cubed plus 6x squared minus 8. So this is the derivative of our problem. And I always go back to this, but just to be clear, so if I had graphed this function, this insane function of loop-de-loop polynomial, then if I wanted to know the slope of the tangent line at any point, it would be by plugging that value of x into here. So nothing has changed with the derivative and what it means, but that is the derivative of the function. Okay, so let's pick up the skill level a little bit here, and I'm going to do that a lot. We're coming up. So 4 over 5x minus 1 squared. All right, so most students, and rightfully so, are going to look at this problem and hopefully go, oh, it's the quotient rule. This is true. We could use the quotient rule in this problem. No issues there at all. But as I've stated before, let's say we were given like y is equal to 2 over x to the 5th. What I've stated before is using the quotient rule for this is a waste of time. Why? Because we can change this to 2x to the negative 5 and do a simple power rule with a constant multiple, and get a super simple easy derivative and be done with it. So it turns out that this is a quotient rule that has a constant in the numerator, so we can change this to 4 times 5x minus 1 to the negative 2. By doing so, this allows us to follow through with essentially the chain rule. So this is a little bit crazy, but just to show you. So 4 is a constant. So 4 basically just sticks along for the ride. It just hangs out, right? So actually, what I'll do is I'll do it all in one step. So what do we do then with the derivative? We take the derivative of the outer. So negative 2 times 4 is negative 8. We bring along the inner function along for the ride, and then we subtract 1 from our exponent. So if this had been, let's say, 4x to the negative 2, all of you would have been like, oh, negative 8x to the negative 3. Well, look at what we have over here. We have that. We just happen to have 5x minus 1 hanging out while we go ahead and do our business. So that's that. So derivative of the inner function, which is 5x minus 1. Okay, we can do a little shortcut here. This is just 5. Therefore, if we multiply this 5 times the negative 8, we get negative 40 times 5x minus 1 to the negative 3. Ideally, we do not leave negative exponents, so we would write negative 40 over 5x minus 1 to the positive 3, which is our derivative for our function. Okay, so number 7, this is a toughie. So number 7 is a lot like number 4. Notice that when we rewrote number 4, we ended up with a composite function within a composite. So sine 3x is a composite function, but we're putting it within another function. So look at this. So e to the cosine x is a composite function, but where is it? It's actually inside tangent. So whenever you see that, then you're probably going to do a double chain rule. I usually don't go beyond double, by the way. It's usually a little bit too complicated. So, but this looks like it'll be a perfect example of a double chain. So how do we do that? Well, in the beginning, this is clearly the outer and this is clearly the inner. So what does that look like? Well, we have to find the derivative of tangent. So everybody should have memorized the derivative of tangent is secant squared. We then bring the inner function along for the ride, and we're good to go. Secant squared of e cosine x. Then we multiply that by the derivative of e cosine x. Okay, but when we do that, we basically look at this and go, oh no, this is another chain rule because it's cosine within e. So how do we go about doing that? Well, we have to take the derivative of the outer function. Well, what's the outer function? It's e. Well, e, the derivative of e is e itself, and then we bring cosine along for the ride. So I know that looks weird because it doesn't look like we did anything, but we did. The derivative of e is e itself. Then we multiply by the derivative of the inner function, cosine. This we can find. The derivative of cosine is negative sine x. So what do we have right now? We have this, and this that all have to go together and create a final function. So this is not easy to write, but what I would suggest, because this looks so crazy looking, I would move the negative sign to the front. I would put e cosine x next, and then I would write the secant squared of e cosine x last. Why? Because if you put any of this stuff over here, it's just going to look really weird. I mean, you could technically have e cosine x right next to e cosine x. Students would get super confused because they're going to be like, wait, do I do e cosine x squared? And you can't because e cosine x is inside this function and can't be moved. So this is basically the answer to the problem, which is yes, insanity, but that is the derivative of the function using a double chain. So this is double chain. And if you want to make a note of that up here, you can double chain, but that is the process so far. Okay, so the last page of section 3.7 here is the the crazy page. So I'm going to read this, and as you start to get nervous, it says, finally, don't forget about the product and the quotient rules, as they will pop up in chain rule problems often. The ultimate key to differentiating functions with multiple rules is to determine which rules are applied first. Okay, so this should sound familiar. In the product and quotient rule section, I think it was 3.4, we talked about doing one or the other first. So now we have a third rule that also is in part of what we have to do. So now when we find the derivative, we have to determine which one goes first. Okay, so look at number 8. So I'm asked to find the derivative of e to the x squared plus 7, 3 to the 2x minus 5. Hopefully, you clearly see that there is a multiplication sign here that's not being shown because these are just happen to be right next to each other. So the key is in class, what I would ask students is, what two rules do you see in this problem? So what I always get the correct response, always, want both of them, but they will say, I see a product I also see a chain, specifically 2 of them. Okay, so the product I already marked, right? But if you look at each one of these functions, which are basically f and g, each one of them has a function composed. They have a function inside of them, which means we have a product and 2 chain rules involved. So, but the real question is, in order to get this problem correctly derived, we need to determine which rule goes first. So my question is this derivative on each of the chain rules right now, or is it on the entire product? This is a little bit tough for students, but the right answer is that it's on the entire product. It is, right now we do not see this. Okay, we don't see this. Okay, hopefully you're not seeing this. So this, I don't see this right now. So the derivatives are not on the individual chains. They're on the entire product, which means that we need to do the product rule first. So what does that look like? All right, so remember, again, FG here. So product rule. So product rule is f prime g plus fg prime. So we're going to do and write it out. We're going to do the derivative of our first function, e to the x squared plus 7, times our original second function, g, plus our original first function, times the derivative of our second function. Okay, so you'll see that right now you're going to understand why these ddx's are so important, because students are going to try to shortcut the process and they're going to make a mistake. So what I do here is, instead of writing this out and becoming an insano problem, I do the same shortcut process that I've been doing, and I'll do it in a different color so you see it. So what do I need to do? I need to do a chain rule for each one of these derivatives. So as an aside, I am going to create another dx in the problem. So you need to identify e to the x squared plus 7, e specifically, as the outer function. So what is the outer function derivative? It's e to whatever. Well, the x squared plus 7 comes along for the ride, and we multiply by the derivative of the inner function x squared plus 7. What about over here? Again, what is the derivative of 3 to the 2x minus 5? Well, we have to return to our simple derivatives. Whenever we do the derivative of b to the x, that is always equal to b to the x natural log of b. Okay? So what does that look like in terms of what we're doing? Well, we have to find the derivative of 3 to whatever. So 3 to whatever is going to be 3 to the inner function coming along for the ride, natural log of 3. So note, it's the same thing as this, with the 3's here and here, except the inner function comes along for the ride where the x is. Then we multiply by the derivative of 2x minus 5. Now, I'm readily aware that some people's brains are going to sort of look at this in the beginning and go, woof, like, woof. And I'm also aware that some students are just going to write 3 to the x natural log of 3. That is wrong. Remember, wherever you see x, the inner function must follow. Just like we did here, where the inner function followed e to the x where it went. So make sure that you do that when you're doing the problems. So again, what we can do as a shortcut here is we can find the easy derivatives, make sure all the derivatives are found before you actually move on and put it all together. So what does that look like? So right now we have this, this, and this that need to be put together on the left side. So we can put them 2x in the front, so we got 2x. We have e to the x squared plus 7, and we have 3 to the 2x minus 5. That is the left side of the plus sign. What do we have on the right side? We have this, and we have this. So what would be the best thing to do here? Well, I don't know if there's really a right way, per se, but I usually put the constants in the front. Well, the constants are here and here. So 2 natural log of 3. Then we got e to the x squared plus 7. 3 to the 2x minus 5. Okay, so right now, hypothetically, this is the right answer. But as you've seen in the past, when it comes to MyMathLab and various solutions, we often factor things out, and it turns out we can factor out a lot. So you can see there's a 2e squared to the plus 7, 3 to the 2x minus 5, all in common. So you're actually left with just x plus natural log of 3. So you find this more often in textbooks as the answer because it's a little simpler to write and to graph. Also, if you need to plug in a value of x, would you rather plug it in here or here? By a mile in the second one, because there's much less x's that you have to deal with. Okay, so what about number 9? So number 9, here we go. The derivative of the quantity x cubed plus x plus 1, x squared plus 1, all to the 8th. All right, so again, what do students I often ask students is, what two rules do you see? And again, what they give me is product and chain. Well, where do they see the product? They see it right here. Where do they see the chain? Well, this whole thing is to the 8th power, so this entire thing right here is an inner function. But the real question is, which one is the one the derivative is on right now? Hopefully you'll see that it's the complete opposite of this one up here. The derivative is on the 8th power, which is the chain rule element of this problem. Which means if we need to find this derivative, we have to start with the chain rule. So how do we do that? Well, and don't get all like thrown off by what's inside here, right? So this could be overwhelming just to look at, but don't get thrown off. Pretend it's like 3x plus 1 or something. What would you do in that standpoint? You would take the 8, the outer function, you would move it to the front, you would still get x cubed, the inner function coming along for the ride, right? This entire thing coming along, and you would subtract 1 from the exponent. Then you would multiply by the derivative of x cubed plus x plus 1 times x squared plus 1. Okay? So then you would look over here, hopefully, and you would go, oops, that is a perfect example of the product rule. That's a very glitzy color. So if we need to do the product rule, believe it or not, we have to do the whole rule for that whole scenario here. So let's do it as an aside. So remember, this is f and g, right? So we have to do the derivative of f, which is our f function, which is x squared plus x plus 1, times our original function g, plus our original function x cubed plus x plus 1, times the derivative of x squared plus 1. Again, find all the derivatives and determine them. 3x squared plus 1, 2x. Alright, so you see the dx's are all gone, so we now can go ahead and take all our results and put them together. So our results for the right are here, here, and here, and there. And then our results on the left are clearly here, so of our multiplication. So we have to put it basically all together. So it's going to be enormous. So all we're going to do is copy this side. We already found this part of the derivative, so nothing to do. Just like in all the previous problems. Then we're going to write out this entire thing. 3x squared plus 1, and we need a bracket here. 3x squared plus 1 times x squared plus 1 plus x cubed plus x plus 1 times 2x. Now, I'm actually going to change this up a little bit here. So this 2x should go in the front of x cubed plus x plus 1. So here, there. And we get this as a result. So unlike other chain rule problems where you do have to do a little simplifying, please don't do that here. This is a pretty crazy problem. I don't want you to simplify this. Similar to the quotient rule insanity, even though we didn't use it, this is perfectly fine. And by the way, on the lab, you will have some problems, maybe not to this extent, but you're going to have problems where you're going to get this monstrosity in there. Don't simplify that. It's perfectly fine to leave it when you have all those quantities. But this, believe it or not, is the derivative of this function. Okay, so last problem in the chain rule. This is also, all these sections are so long to get through, but here we go. So if you look at 10, what two rules do you see? That is the question I usually ask in class. So students immediately blurt out usually quotient because they see a fraction. And note, the numerator is not a constant, which means we can't do any quick funny business where it comes to this stuff. So we can't turn it into something really easy. So that's out the window. We have to go straight quotient. And then usually students will be like, well, I don't see a product, but if you look at the denominator, there's clearly a chain involved with it. Okay, so this is a quotient and chain. Now the question again is the derivative on the quotient or is it on the chain? Well, this d dx is not down here, right? It's not down here. That would be on the chain. So therefore, if you look at this d dx is on the entire quotient, so we must use the quotient rule first. So remember, with the quotient rule, we treat the numerator as f, the denominator as g. We're doing f prime g minus fg prime all over g squared. So let's go ahead and do that. So we're going to get the derivative of 5x minus 1 times x to the fourth plus 2 quantity cubed minus 5x minus 1 times the derivative of x to the fourth plus 2 cubed all over x to the fourth plus 2 cubed squared bracket, right? So that's pretty crazy. So what we do basically is once we get this, then you can look over here and go, oh, that's 5, that's easy. But then when you go over here, you go, uh-oh, that is a perfect example of a chain rule. So let's do an aside using the chain rule. So outer function is the power 3. That goes to the front. Inner function comes along for the ride. 2 as the exponent. We multiply by the derivative of the inner function, which is x to the fourth plus 2. Okay, we still don't have the ending to the problem because we need to find this derivative, which is 4x cubed. Okay, so once we get all of that, we can move on and we can write the result in our problem. So 5, x to the fourth plus 2 cubed minus, we now have 5x minus 1, 3 times blah, 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 and 4x cubed. Ideally, the 4x cubed goes to the front. 5x minus 1 is here, and then 3... oh, I missed on that. So this 3 has to multiply by that 4 right there. So that's 12x cubed. And then we get x to the fourth plus 2 squared all over x to the fourth plus 2. We don't want to rewrite this. What is power to a power? What do we do with their exponents? We actually multiply them, so we end up with the following to the sixth. We end up with the following as our result for our derivative. Let's make this more clear, 6. Okay, so again, you don't have to simplify that. Ideally, you move things where they go to make things easier, but this is the derivative of that function. This page is a doozy, I'm not going to lie. Students, as they go through it originally, go, oh my god, this is a doozy. And then they're like, oh no, here we go again with more, even bigger. So I'm not going to lie, I'm going to be really clear about this at the end of the section. Students really start to struggle when they hit the chain rule, especially students who are, not naturally good at math necessarily. So you just have to follow the process. I gave you everything you needed in terms of the mental process. Obviously, if you don't know your previous derivatives well, it's going to be a fail. So get on your horse, so to speak. Study this like crazy. Know all the derivatives inside and out, and get this chain rule figured out.